Hello everyone, my name is Kevin Starr. In this series of single loop control methods, we're going to be discussing tank level identification and tuning. We're going to combine those in one presentation. So up until this point, we have talked about different types of process identification and even how to tune the self-regulating process. Those are the two primary classes of processes that you'll deal with in industrial applications. Self-regulating are processes that when you do a step input, they stop themselves. And we've talked about those. There's first order, second order, overdamped, underdamped, critically damped, dead time dominant processes. But that's not everything. That's a high percentage. I mean, 80 or 90% of all the loops that you will go and try to tune are in that top category. This bottom one here is what they call non-self-regulating. I'll show you some examples of what causes that, but it's a very different process. You can see here, when you have a step input, it just keeps going and going and going. So if it's a tank and you walk away, it'll overflow or it'll empty. So self-regulating processes, they stop themselves for a step input. For a non-self-regulating process, when you change the input or change the balance, you will integrate one way or the other. So it's an integrating process, and that's what we're going to talk about today. Is first of all, how do you identify the process model and how do you tune it? And these are, I've heard it said that 95% of all tank levels or integrating process oscillate. They do this. And so we're going to talk about how do you identify that and how do you remedy that. This is just a short refresher to show you some of the terms that we've talked about so far. If you've watched all the series, there is a pure gain process that just has a single model parameter. You have a first order process, that's that kind of that step in that first order response. It has two process parameters. There's the process gain and the time constant. Then you can see if there's delay, first order plus dead time. You know, we're going to talk about that, dealing with dead time, in a subsequent chapter. But you have three model parameters. And then we have this guy, which is an integrating process. So you see it's back to a single one. And this is where identification can get kind of confusing. Is a lot of places they'll use the same nomenclature, K sub P. P is process, K is gain. Well, are they the same? How do you deal with that? And the answer is they're not all the same. So the top three that stop themselves, the gain's calculated the same way. Change in measure value over the change in the output that produced it. But how can that possibly be here? It depends on time. If time keeps moving, the change in the output keeps growing with time. So it can't be the change in the measured value over the change in the output. Time has to be incorporated into that particular parameter. And that's what we're going to talk about, and that's what makes tanks a challenge, but I'm going to show you a shortcut that makes them easy again. Now this is an example. Tanks are common examples of an integrating process if the outlet flow is held constant. So typically there's a pump or a controller that is trying to control a constant outlet flow. So if you look at this, you know, if I talk about what's called the first principles or the laws of physics, what governs this tank level? Well, it's the outlet flow compared to the inlet flow. If I have nothing coming in, this will empty. If I have more going in than going out, I'll overflow. So what happens is the pressure head of the level gets absorbed by this actuation device to maintain a constant outlet flow. So what happens is you get a disturbance or you get a change in the input and the output. So if you have the opportunity when you're getting ready to do one of these bump tests, if you have enough instrumentation, I like to actually show whatever's my inlet and whatever's my outlet. And you can kind of, a balance condition is when they're equal. When the inlet and the outlet are equal, the level stops moving. When you have a difference, you have more going in than going out, you go up. If you have less going in than going out, you go down. So that's an integrating process. Turns out that there are some drives where you're talking about amps and torque that follow the exact same process model. But right now we're going to, in this context, I'm going to show you how you deal with this. You have some sort of a transmitter measuring the level, going to a controller. A lot of times they will control another controller that is maintaining a constant flow. Now that we've framed the problem that we're trying to solve, is we have a tank that has a level that we're trying to maintain at some reference point. We're going to adjust, it could be the inlet or the outlet, I've seen it either way. In this example, we're going to control the inlet based upon flow out to maintain a constant level. And why is that important? When you get into tanks, usually you'll see there'll be a an agitation device that's mixing your tank. So a lot of times there'll be a mixing tank. They'll be putting stuff in there and they want to mix it. So if the level is moving up and down, the concentration of, or the consistency of the product will go up and down also, which can cause problems on down the line. We also have to worry about header pressures. A lot of time this level it has several outlets. So if it's going up or down, the header pressure is going up and down, which can be causing problems that permeate through your facility. So trying to figure out how to maintain this level is kind of important. I've also seen the opposite side is if you try to tune this too aggressive, the quick movements of your actuator can cause problems upstream. So there's no one answer to fix all of this, but what we're trying to do is say if 95% of all tanks oscillate, is there a way to fix it? And the answer is yes, but it's counterintuitive. It's not what you would think of when you go to solve it. So in all of these, when you're getting ready to tune a loop, I recommend that you go do a visual inspection. Try to get it in your head. What's the actuation device? What's it look like? How big's the tank? All those kind of things. Get that in your head. Then decide, well, how do I want this to operate? Do I want to have a lot of oscillations, no oscillations? Kind of frame the problem in your head. But as we've been talking about using the direct synthesis tuning technique, you have to understand the process dynamics. So we have to come up with a number that represents that tank. And that's what we're going to talk about. But because tanks have a time element to the measured value, we have to look at slope. So the answer is the change in the slope over the output that produced it. That's the name of the process gain. So if you haven't done slopes for a little while, it's rise over run. So when I cause an imbalance in my tank and the level starts to move, find a spot that's steady state, where it's moving at a constant slope, and take 2 points. So I'm calling them x1, y1 is 1 point, x2, y2 is another point, where y is your level and x is time. So what we're saying here is, if you remember your rise, it's the change in the level, change in y, y2 minus y1, divided by the change in time, x2 minus x1. And that's your slope, m. So, you can do this by hand or do a bump test and try to calculate the slope. But the tricky things about tanks is you have to have two slopes to calculate the process gain. And that's where I've seen people make a mistake. Those are the two places that people make a mistake, is they don't calculate the change in slope. And then the other thing is the units of time have to be the same units as your integral time. I've seen that many times, is your integral time may be in minutes on your controller and you calculate this in seconds. And you'll be very, very off. So the units of your process gain for your tank have to match the time component of your integral time. Now, here's an example. I'm going to show you a simple example where you're walking along and you change your inlet flow for a period of time and then you drop it back down. So we have a balanced condition on either side of our bump. So when the level is balanced, your level is no longer moving. This is how I like to try. If I'm tuning a tank, I'll sit there and adjust the output until I can balance the level. Because what's the slope here? That's a slope of a flat line is 0. So here the change in slope actually is just the slope. So here where our slope's 0, we have a slope, our slope's 0. So this one's hard to mess up. It's just kind of hard to do this. And I will show you another example that shows more realistically what you have to do. And that's where this gets kind of complicated, is calculating all these slopes. And it really is kind of complicated. But what you want to do is try to get where the slope is fairly constant. Look at the slope before and during. And so here I can calculate a slope, this minus this divided by the output that produced it. That's my process gain. And then over here, this minus this and the output that produced it. And that's what I'm showing here, is your change in slope and your change in output. In this case, the slope was 0 before and after, so it was easy. What about this? This isn't necessarily uncommon, and actually it could even be more challenging. Is where I see people mess up is if they don't take the time to balance the level before they start, your level's not flat. So it actually has an initial slope. If you assume a 0 when your initial slope isn't, your gain will be all screwed up. So consider what your initial slope is. If you can make it 0 by balancing the inlet and the outlet, it makes it easier. If not, don't worry about it. So here when I change the output, here comes the level, boom. Now I change the output back down, and then I go back. Now I like to kind of follow this process here where I do the step bump test we talked about in a previous episode, But notice the change in time of the two humps. In this case, I let this one run about twice as long as this. Sometimes it's not always easy to tell if you have a self-regulating process or a non-self-regulating process. If this were a self-regulating process, this would have come right back to where it started from because the output was put right back. Notice here, with it's a non-self-regulating process, when I balanced the signal, my measured value is at a different place. Why? It's because I had a different time element. I like to do that just to kind of help me identify, is this a tank or is this a pressurized vessel or is this a near integrating process? Just changing the time component of your bump cycle can help you identify that in the future. But here you can see the inlet and outlet flows are equal, so we're balanced. Here we see the inlet flow went above the outlet flow, so we had a positive, increase in slope for a change in time. Then we checked the output down, and then the flow was less, so we're emptying the tank, and then we balanced it again. So that's our bump test. This isn't uncommon, and again, you may not have a zero slope if you didn't balance it, so you'd have even another slope. Now we framed the problem, and we've got a picture of a bump test. Now what we're going to do is add some numbers and go through an example. So here what we can see is the outlet flow is constant, and we ran the inlet flow so it was higher for a period of time. So it went from 80 to 100%, and it took from 10 to 30 seconds to do it. Then we took the outlet flow and took it back down. You can see the tank emptying, and we let it do it for a little longer time from 30 to 70, and it ended up at 20%. So notice that I'm using the time units as percent. The time units in seconds, so my integral time must be in seconds, and I'm using percent for my level, so that means I've scaled my level in percent. If it's in units of inches or centimeters or whatever, you may need to do a units conversion to get it into percent. But right now what we're interested in is the slope at each one of these sections. There's 4 sections, M1, M2, M3, and M4. So M1, if you've balanced it, so the inlet and the outlet are the same, the slope is 0. So I purposefully set this up so that M1 and M4 were 0. So those, when you take the change in slope, you're subtracting from 0. Over here, what's slope 2? So slope M2 is going to be the change in the measured value, 100 minus 80, over 30 minus 10, which is the change in time. And it works out to, it's a positive 1% per second. It's important that the sign matches what you're seeing. This is where people have messed up the slope, is if you're not careful with the change in measured value or if you get them backwards. And for example, if you calculated this to be a negative slope and it's going up, you did something wrong. Just stop and go back and make sure that you do it. If you take, the top minus whatever these coordinates are, line them up so that you make them right. The data has to match. So that means that every second this thing goes up 1%. Now when we go down, we can see that the slope going down, it went from 100 to 20. So we're taking the final spot, 20 minus 100 over 70 minus 30. And it works out to a negative 2% per second. Well, so I always recommend that you stop and look at the numbers, and does that make sense? Is that what it looks like? Calculate the slope, make sure the sign matches, and make sure that your little triangle rise over run matches. You have to get the slope right, and I'm going to show you why here in just a minute. But what's neat is once you have that, then you can calculate the process gain. So when we look at the process gain for a tank, it's defined as the change in slope over the output that produced it. Now if we look at this, we had 4 slopes, M0, M1, M2, M3, and M4. And I've kind of set it up so that we balance the tank before and after, so the tank's not moving. If it isn't, then your initial and final slopes may not be 0, so calculate those. And then we see that we calculated our M2 was a 1 and our M3 was minus 2. So now you have 3 transitions. I called them A, B, and C. When you went up, that was the first 1, 2, 3. So what was the change in slope over the output that produced it at A? Change in slope over the output that produced it at B. Change in slope over the output that produced it at C. And I like to do that because if I get the same process gain, then I know I have a fairly linear tank. And we'll get into that in dealing with nonlinearities here in a few chapters. But right now, let's assume that our tank, or the area that it operates in, is fairly linear. So what we can see here is the change in slope. We went from 1 to 0 with a change of 10. So our output here was a change of 10%, so we get a gain of 0.1. Over here at point B, our process gain at point B is it went from 2 to 1. This is where it gets kind of confusing is with the signs. Is basically be careful because you're starting with a negative, but you're subtracting, and then you divide it by a change in 30, and you get a 0.1. And then over here, the change in slope from here to here over the output that produced it. I like to do that and then see if I got my signs right and if I get the same process gain each time. The numbers have to match, and then I'm going to show you real quickly here in a minute what that gain actually means. In this case, we have a 0.1 for a process gain, and that's what you need to use. Is one number is you calculate kind of how much power does your actuation device have on that tank. If you have a tank that is as big as this room and this little bitty garden hose, imagine how long it takes for that thing to be filled. Or vice versa, I have this little bitty tank and I've got this great big fire engine hose. You know, the size of the actuation device as compared to the volume or capacity of the tank is really what we're looking for. Is if I can know when I move this, this actuation device, how much is coming out, that's what I need to identify because that's what I use to calculate my tuning parameters. Once you've identified your slopes and you've identified your change in outputs, make sure the gains match, make sure the signs are the same, but also do another what I call kind of a litmus test and recognize that this process gain is actually related to the fill time of your tank. Fill time is defined by this equation right here, and it's not something that you can do. I mean, maybe you can if the machine is down or the plant's down and you can fill it up if they're doing a cleaning cycle. But the idea is, assume your tank is, is empty. It's completely empty, and you walk up and you take your inlet flow from 0 to 100%. All right? So you open it all the way, and then you let the tank start to fill. So here it takes off. Zoop. And when it gets to the top, you shut the tank, you shut the valve off. So you're basically saying, how long does it take to fill this tank from 0 to 100% at maximum flow, inlet flow? Now, if you're controlling the outlet flow, then it's the maximum empty flow. But the idea is to calculate the amount of time it takes for that to happen. That's what's referred to as the fill time. So I'll show you here in just a minute what the relationship is between this fill time and the process gain we just calculated. But there's a couple of equations that you need to kind of understand. Is the volume of a tank or a cylinder is that pi r squared h, that's the volume. And a lot of times you can get that from the P&ID drawings. Sometimes you actually have to go and look at it. Look at the tank and sort of see what the volume of that is. Where the height is defined as usually the taps. It's a differential pressure or the size of the tank. So you calculate the radius, you can see the radius, you can see the height, you can calculate the volume. So if you know the volume and you know the maximum inlet flow, you can calculate this fill time without actually having to do this bump test. That's what's kind of exciting about tanks is once you know this little trick, then you don't even need to do those slope bumps. It's just more of a validation. And like I said, a lot of times you can walk up to a tank and you can kind of, some guy said once the amount of time it takes to walk around a tank, it should be really close to the fill time. I don't know how that is, but this isn't that hard of an equation, and in a lot of P&ID drawings this is already recorded. So if you know what the capacity of the tank is and you know how fast you can fill it or empty it, you can calculate the fill time. And here's an example of that. So the tank fill time is defined as the volume of the material between the high and low reference points on your transducer for your level transmitter and the maximum flow rate. So basically your volume divided by flow, flow is like say gallons per minute and your volume's in gallons, so you get minutes. So here you can see I've got an example where I got a tank diameter of 6 feet, which would be a radius of 3 feet. The distance between the taps is 5 feet, and I have 100 gallons per minute. For the guys that use metric system, this is even easier. But what we have here is we can calculate the volume. In this case, it's this many cubic feet, that pi r squared h. But we have to kind of calculate our flow. We have to calculate it in gallons. And there's 7.48 gallons per cubic foot. So this tells me how many gallons this is where it's easier in the metric system. It's just a decimal point. But in the English system, this 7.48 is the conversion between gallons per cubic feet. So a lot of times your volume calculates cubic feet, but you need it in gallons because that's what your flow's in. So calculate your capacity of your tank in the same units as your flow measurement. So here we have gallons. That's how many gallons are in this thing. So if I know my maximum flow rate, if I open the valve at 100% and it runs at 100 gallons per minute, then I know that it's going to take 10.6 minutes to fill it. And what's interesting about that is that 10.6 is equal to 1 divided by the process gain. So if we calculate the process gain as we did with the slope calculations, that actually works out to be the inverse of the fill time. So if you remember, that example was a process gain of 0.1. Well, that would be 10 minutes to fill it up. So then I go and look at the tank size, and does that make sense? I always like to rationalize the numbers that I calculate with the physical size of the tank. It has to match. If it doesn't match or you don't feel comfortable with it, don't then use it in the control and hope it works. Go and make sure, does this look reasonable? That this is the right fill time? I've seen cases where they had the transmitter set wrong, or that there's a lot of things. It has to line up. Once you've captured the dynamics of that tank, then you're ready to go in and tune it. Now, you have to, this is showing what happens if you use a proportional only control. You come up and someone makes an outlet change, we have to put a control on this. Otherwise it'll empty or it'll result in an offset. And that's what we're going to look at here. Control is needed, but proportional only control does not work for load changes because it results in an offset from set point. This is a good example of a tank that's got a mechanical device. There's a float here, and this float is hooked to like a gate valve, and so the leverage is what defines the proportional action. But what can happen here is, let's say everything's happy. Here's the set point. Here's my measured value. The inlet and outlet are the same. Now somebody comes up and opens the outlet flow. So you can visibly see there's more going out than going in. So what's going to happen to my tank? It's going to start to drop. As my tank starts to drop, it opens the inlet flow until the inlet flow and the outlet flow match, and then the tank stops. That's what proportional only control is designed to do, is to stop the changing air, but it's not designed to make the error zero. And you can see it manifests itself in an offset. So what would have to happen in order to get this offset to go away? Well, in our example here, you'd have to push the float further into the process, which isn't possible in a mechanical device, but with integral we can do it, because I have to have more volume going in to the process than leaving to get that tank to start to come back up. That's what the trick is. With proportional integral we can do that. Proportional only, you're going to result in offset. Proportional plus integral, you can regulate to a set point, and that's what we're trying to do, and that's what we're going to show you here. The tuning parameters are pretty simple. The integral time is defined as 2 times the arrest rate, and the process gain is defined as 2 divided by the process gain and the arrest rate. So what is the arrest rate? That's going to be the trick. But the arrest rate is defined as the amount of time it takes for the level to stop getting any worse. Okay? So right now let's define that. Arrest rate is defined as the amount of time it takes for the level to stop deviating away from the set point, arresting the level. So you have a disturbance and the level starts to drop. When can I stop the level from getting any worse, and then I recover? So imagine pushing that float further in to stop the level, and then you recover. That's the arrest rate. Now I'm going to give you some hints here in a minute on how to pick arrest rates. But right now that's the definition. So here's an illustration. Remember, the only tuning parameter here is your arrest rate. You pick that. You're tuning it. You define how long do you want this to take. Your process gain, if you have the volume and the max flow rate, you can calculate it on a sheet of paper. If you don't, you have to do the bump test. But your process gain is right here. So you can see, and that's 1 over the fill time. Now, my arrest rate, this is showing it's the amount of time it takes for the inlet and outlet flow to become balanced. Remember, on a tank, when my inlet and outlet are balanced, the level stops moving. It has to. But that's now I have an offset. So what we have to do is define that point. So that's what we're calling an arrest time, or an arrest period. That's the time it takes for the inlet and outlet to be equal. Then what happens is the tuning has to be such that my inlet flow becomes greater than my outlet flow. In other words, how are you going to bring that tank back? You've got to put more in than you're taking out to get the level to come back. So here you can see this goes above, and you can see the level starts to turn around. And then what you see is this trajectory, and when the inlet and outlet are back to the same, our level will be back at the same point. And that happens at 6 arrest rates. Just sort of a quiz. Do you remember how long it takes on a self-regulating process in terms of closed loop time constants to hit the set point? 4. So roughly 4 time constants on a self-regulating process. On a tank, it takes 6 arrest rates to come back. Now in control theory, this is called an overdamped response. It's the fastest you can get back to the set point without having an oscillation. And there's a lot of different tuning rules. Some people like to see this wiggle. I found this to be a very stable and secure tuning technique, and it's pretty simple. Once you calculate the fill time, you just use this equation. Then you pick the arrest rate, and I'm going to show you how to do that here in just a minute. But this is the trajectory. Whether you have a load change, either up or down, you can see how long does it take for the level to stop getting any worse. That's when these are balanced. And then it goes above the outlet flow for roughly 5 more time arrest rates until it gets back. So this is the fastest way to get back to the set point without causing an oscillation. And that's the method that we like to use for tuning. And it's simple. The 2 times the arrest rate over for the integral time, and the controller gain is 2 over Kp times the arrest rate. Now, how do you calculate arrest rate? And this is what I like to do, is define fast and slow as a function of the fill time of my tank. So the fill time, if you remember, that's 1 over your process gain. So that's how big is this tank. So if it has a capacity of 10 minutes, then to try to say I want to have an arrest rate of 20 minutes, that doesn't make sense. That means that I would completely empty my tank for 10 minutes before I even turn it around. So by relating your arrest rate to your fill time, you can bias it so that you don't make sort of incorrect judgments. So I picked this M, just another number, which represents a multiplier. And so a fast response is roughly 5 times the fill time. So you can see that you can specify your arrest rate as your fill time divided by 5. So if I have a fill time of 10 minutes, then my arrest rate would be 2 minutes, and then off you go. And if you want a slow response, roughly 2 times, if I have a fill time of 10 minutes, then I'm going to let it go to 5 minutes before I turn it around. That would be considered very slow. So it's a way to do this sort of fast and slow referencing and defining of your tuning parameters. So you don't just arbitrarily pick an arrest rate. I'm going to show you another equation here shortly, but when you do it in this fashion and you use these factors, it's a little bit like the tau ratio that we used before, where the bigger the number, the slower. It's backwards here. Is the bigger the number, the faster it is. But I like to write this equation out so that my integral time is 2 times my fill time divided by my speed of response, and my process gain is 2 times my speed of response. So it even simplifies it even more, and it gives you a sort of a safe, you don't ask for arrest rates that aren't reasonable for your tank. So this table is a good table to get to know. The other thing I like to do is when I calculate my process gain, again, you can walk up to a tank and a lot of times you can estimate it. So if you happen to know the integral time and the controller gain, if you multiply that, the control gain, integral time, and the process gain, you can tell without even doing anything if the loop is going to work when you turn it on. If that multiplication is greater than 4, it's probably very, very slow. If the multiplication is less than 4, it's probably oscillating. If it's equal to 4, then it's probably tuned pretty well. So this assumes the standard form of the PID algorithm, and you've got all your scales right, and we can talk about that in a different episode. But for right now, you can make sure the units match, and you use these, just multiply those 3 things together, the gain, the time constant, and the process gain, and then compare it to 4. And you can tell pretty fast if the loop's fast or slow. One thing that you'll notice when you apply these tuning rules is they are very different than the numbers that you might use in a self-regulating process. Matter of fact, your control gain on a self-regulating process might be 0.3, 0.4, 0.5. On an integrating process, it could be 10 or 12. So it's different by a factor of 10. And a lot of times, if you haven't sat down and done the due diligence and you're used to tuning all these self-regulating processes, you just start with those numbers and your tank will oscillate violently and you won't really know why. So having a method to follow, a tuning technique to follow, can allow you to get to the answer and a much more stable result. I was telling you there's another way to come up with your arrest rate. And I've used this one as well, as sometimes a customer will say, for a given load change, if I have a load change of 20%, my level can't move more than 2%. Well, with this equation, you can calculate the arrest rate from this. It takes a little bit more math, but you can calculate, if they tell you what your max deviation is, you can calculate the arrest rate. And so I'm just going to leave that here for you to look at as we can go through an example. Is if you know the load change and you know the maximum deviation, you can calculate the arrest rate understanding this information. The other kind of a warning, I guess, when we're talking about this tank level tuning is this designed for disturbance rejection. So when the customer goes and changes the set point, because the process gain or the control gain is so big, you can get a hit on the output very fast. So we recommend that you put in a ramp rate on your set point. So it's called, these are the cases here, is how do you deal with that? Is by putting in a set point ramp rate, turn set point tracking off, or increase the arrest rate. That will cause the set point delta to be a little smoother, which will reduce that spike in the output. So here, if you have one inlet flow or several inlet flows, or you'll have one that you control and a lot of wild ones, you can't worry about the wild flows. The only one the controller knows about is the one that it's sending a set point to. So what you want to do is, how does this thing change and how does it affect the level? So that's the slope. You have to calculate the slope. But when you do it, you can do things like this, is you can have your tuning parameter set and you can set your arrest rate. So I recommend that you do a validation step. After you've tuned it, after you come up with your slope, after you've picked an arrest rate, whether by deviation or arrest rate, once you know that, then change the load and see what happens. You want to make sure that within one arrest rate, the tank stops getting any worse, and then in 6 arrest rates, it comes back. I'm just reminded of a case where one of the first tanks I got to tune in this manner is the field or the customer was like, I just can't believe this will work. I said, well, sure it'll work. And I'm crossing everything I can cross. And we calculated the slope and put all these numbers in. And as soon as we put it in, it got really flat, which was exciting. But then they had disturbance. The whole machine shut down. And they said for years, when this system came back up, we would have stuff go all over everywhere as a result of a startup. And I said, this will work fine. This technique will work great. And they're like, well, let's see. So again, I'm crossing everything I can cross. And when the machine came back up, the tank level followed this exactly. And I was able to tell them it should hit, I knew the arrest rate. So and it started deviating. Everybody's getting nervous. I said, no, it'll stop at this time. And everybody was excited. And then they're like, and I said, then it'll take 5 more and it'll come back. And it followed it just like it was a simulator. And people thought, oh, that's amazing. And of course, inside I'm like, yes, it worked. But it always works. Control theory works. When it doesn't work, there's something wrong with your actuator, your time units, your maybe the shape, maybe it wasn't linear. And that's what we're going to talk about when we get to the section on dealing with nonlinearities. But this technique, this tuning method, works and provides a very stable input for your control.